guess I have something, I just don't know if it's
Okay.
right.
Let's have a look here. So what problem set was this? Problem set number? Okay, so this is problem set number 4, and it's number 4 from it. Okay. And show the kernel as a subspace. Okay, gotcha.
So I went through the 3.
Gotcha. So the kernel of A is all of those x vectors such that A times x is equal to the 0 vector. Here we go. Okay, so you've got to do those 3 things, right? Yep. First of all, is 0 in the kernel of A is your first question that you have to ask yourself. So then, by definition, well, you want to be a bit more specific about it than this. Okay. Yep. So, so you're absolutely, everything you've set up so far is exactly right. Kernel of A is equal to those x vectors such that, you see, those x vectors such that, that's what that line means, AX is equal to 0. Okay, so the question is, so part A is the 0 vector a member of the kernel of A? That's the question. Alright, so what you say, well, okay, how do you get in there? The way you get in there is if you take A times that vector, the 0 vector. Any matrix times the 0 vector gives you the 0 vector, and therefore that means, this implies then that 0 is in the kernel of A. Okay? I think what you did is you went through the, you had the logic of it. Kim, I don't know if you had the same kind of questions here. So that's why I'm putting it up here, so then we can, you know. What you want to do is, every time, exactly. I mean, you had the idea. It was just like, well, how do you... Exactly, right. Exactly.
Show it.
Yep. Okay, B, so let's have a look at B here then. And then B, is it closed under addition? Okay, so let me just put this back here. Yeah. Is it closed under addition? So you say V1 is a member of the kernel, and V2 is a member of the kernel. And the question is V1 plus V2 a member of the kernel? Okay. So, okay. Now T,
I don't know about.
yeah, here I think you probably looked at an example in the book, and we're trying to, okay. You've got the right idea.
0 plus 0 is 0, so it would have to be. That was my thought.
But here's the deal. What you're saying is, let's go through the kind of the logic. The V1 is a member of the kernel of A. So here's how to kind of maybe think about it. Oopsie daisy. Let me give myself a little picture. Okay. Okay. Here is the set of all vectors that you could possibly have. Actually, this is not a good picture. Let me start again. Okay. So here's your domain space, and here's your range space. Okay. The kernel is all of those vectors that map down into 0 here. Okay. So the thing is, the kernel can just potentially just be 0, or it could be all those vectors on the line there, or it could be the plane through the origin, etc., etc. Okay. So the deal is, you don't know that you've just gone through and proven that 0 is in the kernel, but that doesn't mean that's the only one in there, because I think that's what you were thinking, right? That potentially.
Well, I was thinking that if you transformed it, it'd have to be 0.
Exactly, it maps there, but
but I can't just say the transformation plus the transformation.
You actually can. What you've actually written here is actually not. Is reasonably okay. The only problem is you're saying that V1 is equal to T of X1. I don't know what X is. I don't know what this is. And actually what you really want to have in here is V1. So
I could say V2 or V3 is a transformation of V1? Is that what you would do?
Well, can I?
Yeah.
Let me go back to. What I want to do is I will do the translation language in a sec, but let me do it how you have it defined. I want to use what you've defined as the kernel. Okay. So what you've defined as the kernel is, let me get another sheet of paper, let me go back actually. So, V1 is a member of the kernel. So what does that mean about V1? What's the only thing that you know about V1? What you know is that A V1 equals 0. That's what it means. Okay? So V2 is a member of the kernel of A. What does that mean? That means A V2 is equal to 0. So now your question is V1 plus V2 a member of the kernel of A? Right? Okay, so how do you get to be a member if the sum of them, A acting on the sum of them, equals 0? Okay. So the question is then, so that's the question that you've got to ask yourself and answer. So you just say, well, what does A V1 plus V2 equal? We don't know right now. We'll work it out, right? So you're saying, this is, let me just go through the logic of it. If A on the sum of them equals the 0 vector, then you know that V1 plus V2 is in the kernel, because that's what it means to be in the kernel. So the only question you're trying to figure out is, can I show, what I want to show is that A times this is equal to 0. Okay? That's what I want to show, but I can't. If it's what I want to show, I can't assume it. I've got to start. So I'll start with my left-hand side. And so what do I know? I know that this goes onto this, and this goes onto this. So this is AV1 plus AV2, right? Now, what do I know about AV1 and AV2? The way they were defined is 0 plus 0. Because V1 and V2 are in the kernel, I know that AV1 is equal to 0 and 0, and what's 0 plus 0? 0.
Very close.
Yes.
Not quite right.
That's right.
Okay.
And I think, why don't you try the last one? Except don't use your T stuff, use the A stuff. Yeah. Now the deal is, let me just show you how this could have worked with T's. What this is saying is V1 is a member of kernel of A. What does that mean? That means T of V1 is equal to 0, and T of V2 is equal to 0. And then this down here translates to T of V1 plus V2, which is what you had.
So I had everything, I just, for some reason, put X's in.
Yes. Yeah, but
Makes no sense.
but it's whoopsie daisy. Yeah, so but it's very important to really follow that logic. Okay, so that you start here and say, well, because it's a linear transformation, it means it can act on each one. And then I know these are 0 because of the way they were defined, and that gives me 0. That means this is in the kernel.
Okay.
Okay. Give C a shot and see. I think you should be able to do C by yourself, because that will help you understand the process from B.
Okay. And I use the K's like that. Just go through.
Yeah, but I think, to be honest with you, it's easier to do the matrices, at least for me.
Yeah, I mean, that makes more sense.
Yeah.
This is confusing.
Yeah.
And then,
Let me just check and see how everybody's doing. Good.
I should jump.
Whoops, hold on. Yep. Yes, Dawn. Okay. Let me just answer Dawn's question here. Oh, okay, good. Thank you. There we go. Number 44. Okay. Okay, so basically number 44. So in this problem then, what we've got to do is consider the problem of fitting a cubic through the given points. Okay, a cubic is a curve that looks like this. If k is any non-zero constant, then the equations find the same cubic. Okay. Alrighty, so what did you guys do?
I thought you were just looking for kind of like the other problems where you're just trying to find which ones are independent. So I was putting in the X's and the Y's and then writing out the equations for the, I thought there was 3 that were independent. Oh, that was in 45 I was trying to do. So for this one there would be 3 again. And then I was getting lost. I did all kinds of stuff, but nothing.
Okay.
I didn't even know where to. So I was writing like 1 C1 plus 1 C2 plus 0 C3 blah blah equals 0. And then trying to figure out which one depended on the other ones, but
Yeah, I think what you're trying to do is put the x. Okay, let me have a look. Off the top of my head, I'm not exactly sure what we have to do, so let me just kind of work our way through this and see what probably should end up giving us an answer here. What I'm thinking we would do here. Yeah, what does the answer say?
I did 45.
Oh, okay, should we do 45?
Sure. Then we know the
We
answer.
just know that then we know the answer.
Yeah, that's right. Okay, what does the answer say here? Page number 3, right? The answer is x squared minus x. That is the answer? Okay, all right. I think we should be able to get there. Okay, so when I look at, which is the first point here, right? 0, 0. Okay, what that says to me is that when I take my function, okay. So what I would do is f of x is equal to c1 plus c2x plus c3y plus c4x squared plus c5xy plus c6y squared plus c7x cubed plus c8x squared y plus c9xy squared plus c10y cubed is equal to 0. Okay. So when I look at this, I'm seeing this is an x and this is a y. So what that means is when I put those x and y values in, so my very first equation that I get would be c1 plus c2 times 0 plus c3 times 0 plus c4 times 0 squared plus c5 times 0, 0 plus c6 times 0 squared. You kind of get what I'm doing here? Okay. Equals 0. So if you go through this whole process, you actually see that all these terms go away. C1 is equal to 0. Second equation.
Well, that's what I kept doing, but I couldn't. I wasn't.
Right? Because then
I wasn't getting.
x is 1, y is 0.
Okay, so one is
So it's C1
that's all
plus
one is
C2 plus anything with a y in it goes to 0, right? Okay. And the thing is, you know what C1 is already, so kind of get rid of it. I'm just trying to make my problem easier as I go through. And so what am I going to get? I'm going to get C2 plus C4 plus C7, anything with a y in it goes to 0, equals 0. So that's one equation that I have now that I need to satisfy. Okay. Then I put the next number in and the next in, and I'm assuming that you're eventually going to end up with a kind of a big system of equations, and then you have to solve that big system of equations. Right? So, I mean, notice how they've, well, except for the last two, they all have zeros in it, so it kind of is helpful, but it looks to me like you're going to end up with a 9, how many points have you got here?
So you can't just say for 2, 0, that's just 2 times what you had for 1, 0?
No. Okay, let's go through that. So when x is equal to 2, because you're putting the square in there, does that help?
Yes.
So, you know, I kind of, when I looked at this problem, it didn't look as horrendous as it now actually starts to look, but you've now got a big matrix to look at.
Okay, well that's what I was doing, so that's probably why I wasn't getting.
So I guess the first thing to do is set up your matrix, and then what we can do is go online maybe and solve it with the, it'll actually be probably an easy one to solve my guess is what's going to happen is you're going to get lots of, it's going to be very sparse. There's going to be lots of zeros and only a few things to worry about. So you can actually probably do it by hand. But we can go online and see. Let's try 45, and then we can go online, solve 45, and then see if we can get the answer, and then that will help us with 44. Okay. So if you have a look at your assignment, okay. The very first one here is you wanted to subtract this row from this row here, right? Do you have that in front of you?
Okay, yep. I actually, yeah, -1.
Yep. Right, yeah, minus. So in other words, you go minus and add, right? Is that how you do it?
Yeah.
Okay. So I agree. -1, add to that gives you 0. That's good. -1, add to that gives you 0, which is good. -1, add to that gives you -1, which is fine. But then -0 gives you 0. Add to 3 gives you 3. Okay. So this here needs to actually be 3.
Okay. Yep.
All right. So I just want you to be careful because I think probably what you did is did minus that and then just put it down there or something like that. I'm not sure. But be careful of that because in these big long things it can make a huge, mess. So just be careful about that one. All right. So that was one point to notice. Then let's move on to, down here to this one here. We are actually writing out the solution. I think this is 2C.
Okay.
Okay. So I agree with your writing these out like this, you know what I mean? Like translating it into kind of variables instead of leaving it in the augmented matrix. Now, but what you've done here is you see this guy here. If you write this down, this is 1x1. That's your pivot variable. You put your pivot variables all on the left-hand side, right? Kind of going down here. But then you take all of these on the other sides. And yes, I agree, it's a free variable. So what you do is you say that this equals 1. But you see how it's +1 4x? Then on the other side it becomes -1 4x. x4, I should say. So you have your numbers column, and then you have your free variables. Like that. Hold on, is that not focused?
Okay, I didn't know that it went to the opposite when you brought it over.
Ah, that's better. Here we go. Good. Sorry, I just had to focus that a bit. Yeah, because what you're doing is, I think what you were doing before is just taking this and just saying this is what goes down here, right?
Right.
Yep. But think about it not so much procedurally, but algebraically, as in you have this equation here, and then that goes onto the other side, you know what I mean, like you would in normal algebra. That's all I'm doing here. I'm not, in other words, you know how you've got all these fancy procedures with the matrices? Those fancy procedures are in the matrices, but the moment you write it down like equations, then you're just back to your ordinary algebra. Okay? So, yeah, so that's what happens is you do that, and then here for this one, then it will be 1x2 will equal, you've got the 2 already there, and then -1 4x becomes +1 4x over there. Okay? Because what that does is it makes this minus, plus, plus, something like that. So it changes this thing here. Alrighty?
Yep.
Okay, good. So other than that, that's good. I mean, you've got the free variable, you've got this idea, this is correct. You know what I mean? For your free variables, when you put x4 is equal to 1 lot of x4, that's correct. It was just the signs of these. Okay, good. So I'll carry on. I'm just going to keep working through your assignment, and anytime I see a thing, I'll let you know, okay?
Okay.
Everybody doing okay here? Okay. You guys, if you want to, you can come up here and use that linear algebra thing if you want to solve it. Okay, Dawn, let's have a look at problem number 4.
Okay.
Okay. Yeah, this one here. Okay, all right. So here, yep, everything is good. But what you want to do is the following: is that you want your z, you want your, you see, I think of these as numbers, and then these are free variables. You know what I mean? And we could have 1, 2, 3, lots of free variables. So the number z is equal to z, right? So that's okay. So that means 0 plus 1z. So now what you have is when you're writing down your answer, if you have 3 components here, these vectors have to be 3 components. You can't lose a component somewhere. Okay. So then this is 13 minus 8 and 0. And then the z is minus 10, 8, and 1.
Okay, I wasn't sure what to do with those free variables, so okay, that sounds good.
Does that help? Okay. All right, good. Yeah, so Dawn, I think as you're going through your assignment and you're having questions like that, you can just send me an email and just say, hey, what do you think about this? And then it can just help kind of as you go through. So don't worry about sending me an email. Whether I respond within 24 hours or not, that's a different question. But just send me an email and I'll do my best, okay? Dawn, let's have a look at number 6 here.
Okay.
Okay, so my question is, where did this guy come from? I'm just thinking, does your book, does it have this in there as well? Let me have a look here. What page is this? Page 18, number 6.
No, I copied down the problem wrong. I looked half at number 6 and the bottom half at number 7. I'm sorry.
Ah, yeah, I get you. Yeah, okay. All right. Okay, so that's what, okay, I was just curious what happened there. Okay. Yeah, be real careful with that, especially like in the test, because it's very easy with these numbers. As Michelle here in Fayette would say, right, you got matrixed out. So it is true, it's easy to get matrixed out. All right. Okay, thanks, Dawn. Okay, Dawn. Let's have a look at number 11 here.
Okay.
Okay, so fine, we've got it down here. We're down here, and you see you end up with a row of zeros. Now, usually what happens when you end up with a row of zeros, that's fine, or you can get down to here, so it's fine. What you want to do now is zeros should always go down to the bottom. In other words, you want to swap these two. Okay. So then what you're going to end up with is, if I do that, let me just write this over here. 1, 0, 2, 4, minus 8, 0, 1, minus 3, minus 1, 6, 0, 0, 0, 3, minus 12, 0, 0, 0, 0, like that.
Okay, then you make the 3 a 1.
That's right, so we'd multiply by a third. Okay, so I'm just going to do that now. Okay, and so now what you see is I've got pivot, pivot, pivot. I've only got one free variable. Does that make sense?
Yep, sure does.
Because I think, I'm just trying to look down here, I think what you did is, yeah, because what you did here is you introduced one more free variable than you actually have. Okay, so actually in this problem you actually have only one free variable, so the answer down at the bottom is going to be something like blah plus r times blah. Okay, rather than the 2.
Okay.
Okay. Now, the other thing is I just want to point out, you know how you've got x3 and x4 here? That's okay, but usually we write them as, you know, R and S, and we say R and S. But remember the real numbers. It's just kind of it gets you, the reason you do it is because when you're thinking of x's, you tend to think of equations, and then when you're putting in R and S's, you're thinking of solutions. It's just a way of differentiating the two. Okay?
Okay.
Okay, thanks, Dawn. Okay, Dawn, let's have a look at this one here. Number 5.
Okay.
So what happened down here at this down here, Dawn? I'm just curious what you are.
I don't know why I didn't divide by -4 there.
Yeah, because then you'd go to 1, 0, 1, 0, 1, 1, 0, 0, 1, 3, 2, 5, like that. And then you can work your way back up, getting rid of this, you know, these two, for using this one below. Does that make sense?
Yep, I see that now.
Yeah. So because you see what will happen is then you're going to end up with something that's going to look like 1, 0, 0, 0, 1, 0, 0, 0, 1 with some numbers here. And you see what you're going to end up with then is just a unique solution. Okay, so yeah, be very, very careful about this. Make sure you you always, here's the deal, here's the thing to remember with these, you know, when you do the RF, okay, you always, every row has to start with a 1. That's the rule. So you always come back and check and say every row has to start with a 1, and it has to stair-step its way. It kind of has to, like that, all the way down with the 1s. If you check that, then you know you've got your RF right. Okay? Okay, I'm going to carry on. At number 7 on page 6.
Okay.
Okay, this is to do with the industry and, you know, one giving products to each other. Okay, do you want to get the, can you go to your book just so that you've got the same page, so make sure we're looking at the same thing.
Okay, I have it.
Okay, so I'm not sure how you set this up, I guess.
I was just trying different things. I didn't know how to set it up.
Okay, all right, so let's try over here. Here we go. Actually, let me try down here. What you really want to do here is just look at the output of each industry. The output for industry A, and then similarly the output for industry B. Let me just see if I can. Whoops. That seems clearer. Okay. So the output for industry A, okay, so if you have a look here, let me just remind myself, okay, that what happens is the output from A is, in other words, what's going out of this box, right? So what's going out of this box is 1,000 and 0.1b. Now, what that means is the output A is equal to this plus this. So in other words, what you end up with then is your output from A, or little a is your output from there, is equal to the arrows going out. So it's 1,000 plus 0.1b. And then for industry B, you're saying little b is the output, the total amount it puts out. And so what you have there is the arrows going out this way are 780 and 0.2a. So 780 plus 0.2 is b. Now you have your system of equations, and now you can go through and do your stuff. Does that make a little bit more sense?
Yes, it sure does.
Okay, so that's kind of the easy way to think about this. Is it's a weird looking diagram, but if you can just think of the arrows going out is what equals to A, and the arrows going out is what equals to, wherever that industry is, that's the easiest way to do it. Okay? All right, thank you. Let's have a look here. I'm looking at page 20, number 37. In the 4th edition book, it's this problem here with industries. Did you have that?
No, I couldn't find that number.
Okay, that's because of your addition. Okay, so what this is just a more complicated industry one, and what you can see is with this particular one, it's exactly the same as the one we just covered, right? So you have X1 being the output of industry 1, you've got industry 2 and industry 3. So now you've got 3 industries and then a consumer using the power or whatever it is they produce. And so what you do is X1, now you just look for all the outgoing arrows, right? So X1 is this outgoing arrow plus this one, and then you'll end up with 3 system of equations. So it's not any more difficult than the other one, except the other one just had 2.
Okay.
Okay. Let's have a look here. These are the ones you just asked about today, right, I think?
Yes.
Okay.
I was confused on this.
Okay. So the idea there here is X is a matrix. Okay. So what you're trying to do is find out what the elements of that matrix are, such that when you take this times their matrix, you get 0. So what this implies then is 1, 2, 2, 4. That's an X is going to be, you see how this is a 2 by 2 matrix, and this is a 2 by 2 matrix at the end? So what that means is you've got X, question mark times question mark, right? Some matrix in between. The first thing to do is figure out what it's, what is this question mark and this question mark? Well, these two have to be the same, right, for this thing to work. So then that means this has to be a 2 by something, and then these two, you tend to think of these two kind of, as long as they're the same, they cancel out, and then you're left with a 2 by question mark, and because the thing that it equals to is a 2 by 2, that 2 is that 2, the question mark also has to be a 2. So that means the matrix in here has to be a 2 by 2 matrix. Did that make sense?
Yep.
Okay, so what I'm looking for, therefore, is my X is a 2 by 2 matrix, and so it has X1, X2, X3, X4, has to equal 0, 0, 0, 0, like that. Okay, so what you've got to do now is solve this equation. Well, if you look at this, if you write it out in the long way, let's actually do the multiplication. So it's this, we'll do this and this, right? Multiply those two together. So that's 1x1 plus 2x3. That times that gives you the first part of it. And then we're taking this times this to give me the second part of it here. So it's 1 times x2 plus 2x4. And then this times this gives me 2x1 plus 4x3. And then this times this gives you 2x2 plus 4x4. And that has to equal 0, 0, 0, 0, like that. Does that make sense, Dawn?
Yes.
Okay. So what you see now is this guy here has to equal this. This guy here has to equal this. This guy here has to equal this. And this guy here has to equal this. So what this does is sets up a big system of equations. Right? So 1x1 plus 2x3 equals 0. That's that one. And then 1x2 plus 2x4 equals 0. And 2x1 plus 4x3, that one there, equals 0. And then this one here, 2x2 plus 4x4 equals 0. Okay. Now, what you have to do is kind of arrange it nicely because, what you want all your, what I would do is now make an x1 column, an x2, an x3, and an x4 column. So this one here is 1 lot of x1 plus 0 lots of x2 plus 2 lots of x3 plus 0 lots of x4 equals 0. Can you see how I'm setting it up as a system of equations?
Yes, I do. Yep.
And then what you do is you just simply go through and solve that system of equations. Okay.
Okay.
And then once you get your answer, once you figure out what your x1, x2, x3, and x4 are, well, then you can put them back into here. And so your solution is x is equal to, let's say I go through and I solve this. Let me just show you. What I'll do here, Dawn, is I'll fax you through what I did for number 55, and I'd like you to go through like number 56 and make sure you know how to do that.
Okay.
Okay, so let me do that now. Dawn, did you get that fax coming through?
I did.
Okay. Why don't, before we go on to that, I think this is what I'm going to suggest. I don't think you're going to have enough time to do the test today. Wouldn't you agree? I think you've got a fair few things to kind of make sure you're okay with. What I would suggest is that I think we're probably going to have to do the test on Thursday for you for this problem set. Okay. What I'd like you to do, I think, is to go through and, the things that we've discussed today, make sure that you're good with. So what I'm going to suggest then is, why don't you do the following, 56, 61, 62, like these ones here, 56, 61, 62, 63. Can you redo those and then send me those, maybe tomorrow when you've done those, just so that you've got those done. Okay. So, okay, so let me just write this down. I've got to remember. Okay, so we're going to redo 61 through 656, I should say. Okay, do that. Then, let me have a look. Okay. Hold on one second here. Let me just figure out. Can you do number, the industry one, number 20? Do that one again.
Yes.
Just to make sure you're okay with that. So this is number 7, page 6, number 20. Okay, good. And for you, just for your own internal, making sure you know how to do it, do those other ones, just to know, so you know how to do those. Then Okay, so now let's have a look at, let me zoom out a bit here. This exercise here. I'm getting a different thing. I'm not sure what you had in your book there. So, on page 88, if you can turn to page 88 of your book. Exercise 1. Just trying to figure out what you have on page 88.
Okay, my exercise is 2.4 actually starts on page 89.
Okay.
And that would be...
Is that number 1?
Yeah, it looks different than that.
Okay.
It doesn't.
So what we're going to do now is I want to go through and just, for the rest of the problems, let's make sure that you've got the right problems. Okay. Then I think you're going to need to get a new book. Because I think it's not going to...
Okay.
Yeah, I mean, I don't have the 3rd edition, or I don't, you know what I mean? So I don't know how to translate for you or anything. So you're definitely going to need to have the 4th edition to make it work. Okay, so why don't we go through then these questions, and I'll get you to copy them down. Hold on 1 second here. Oopsie daisy. So, yeah, so 2.4, 1, 5, 12, 15, right? So here we go. Let me see if I can get them. Actually, let's do the first ones first. If you can copy these ones down. Let me zoom in here. Okay, so there's number 1. So the idea with these matrices is you're just trying to find their inverse. There's, if it exists, 1 and 5.
Okay.
And 12, 12 and 15. That one and that one.
Okay.
And then let's just check the rest here. Exercise 2.4, number 17. Number 17 is this guy here. And what you're trying to do is find if the inverse transformation of this exists. So what you do is, so what do you want to just copy that down first of all? Let me see if I can zoom in a bit. That's about as good as it gets. Whoops. Okay.
Okay, I have it.
Okay, and so the idea with this guy is you convert this into a matrix. Let me just show you. With this guy, you've got something like, you know, y1 is equal to, I don't know, I'm going to write down some random numbers, x1. Something like this. What you do is you write this down as a vector relation, right, where this y is equal to y1, y2, and the x is equal to x1, x2, like that, and the a is equal to the coefficients 5, 2, 3, 3, like that. And you try to see if you've got an inverse for the matrix A. Does Do you see what I'm doing here? This is the equations you've given. You write them in the form y is equal to ax. So a is just the coefficients. 5, 5, 2.
Yep.
Okay, and then what you do is now that you've got it like this, you can use matrix algebra. So you A inverse on both sides. You find out if an inverse for this guy exists. And if it does, you can multiply both sides by the inverse. So A inverse times A means those cancel out. And you get x is equal to A inverse y. And that's how you're meant to do that problem. And then you know what A is, you know what y is, do this multiplication, and you can get out your x. Okay, so that's the idea behind that problem. Okay.
Okay.
What was the next one? Oh, okay. I think you did 11. Let me have a look at 11s here. Okay. I think you're okay with those ones. Let me just check.
Do you have number 19 for the 2.4?
Number 19. Number 19, 2.4. Gotcha. There it is. Can you see that one okay?
Yep.
You can print that, Michelle. It'll be about 20 pages, but you could print it if you wanted to.
What's that?
You can print it if you wanted to.
Where's it printed? Here?
Yeah. You can try. I mean to have got it working now.
Okay, thank you.
Okay, so you got 19, that's right. And I'm just going to check these guys here. Yep. Oh, okay. Okay. Let's just have a quick look here at 11b. I think you've got it pretty close to right there. Just want to get it.
Okay.
Okay. So when you're drawing the 1, 1, 1, 1, and you're drawing that vector, what you want to do is, this is how I would draw it, is it means 1 in the x1 direction, and then when you're here, you go 1 unit in the x2 direction, and then you go, oh, is that what this vector is here? Up?
Right.
Oh, okay. Sorry, I just couldn't see it. That's okay. It's just, with the facts. Okay, I get you. Yep, and then this one is 1, 2, 1, 2, 1, 2, 3, 4, but that one would be like that. That would be AV more up here. Somehow yours is going straight up. You see how it's 2, 2, 2, so you come out 2, you go across 2, and you come up 4. Should end you up somewhere around here.
Yep.
Okay? Yeah, so why don't you do those, Dawn? You can work on those now, and if you get it, if you get it done, you can fax them in to me, that's fine. Or probably by tomorrow, if you can scan them in and then get them to me.
Okay.
And then ask me, and then as you're going through the practice test, if you have questions, send those to me as well, and then we'll do the test next on Thursday. Thanks, Dawn.
Just fine.
Okay, good. And Rick, how you doing?
Just finishing up the last one, and then I'll fax it through.
Okay, sounds good. Thank you. And Dawn, you're just working okay?
I'm good. I do have a question on page 78 when you have a minute.
Okay, yep. I'll just answer Kim's question, then we'll get back to you. Okay, thank you.
I just want to make sure I
Okay.
say the dimensions.
Okay, yeah, let me do the overhead. So do you want to put it down here?
This is what I've done. But it's just determine the dimension of the station and the possible fees that would solve the system. So I just want to make sure that I know. So just finding just the dimension of the solution.
Oh, okay, yeah, hold on a sec. So this is problem set 4. Problem set. It doesn't look right. Jeez, I can't do. Problem set 4, and then it's question number 8. It was really... Oh, it's the wrong way. It'd be nice if this had an autofocus. Okay, I guess. Okay. So for the given matrix A, determine the dimension of the solution and the possible B's that would solve the system. Ah, okay.
I know that you can find like you can find the dimension of like the kernel and the image. I guess I'm just kind of confused between all of these.
Oh, okay. I get you. All right.
I just want to get it clear.
Yeah.
Get all confused.
Okay. All right. I get you. This is a good question. The dimension of the solution is going to be, I'm just trying to think, there's a variety of ways I can explain it, so I'm just trying to go, the simplest one to answer this question would be if you do R ref on this, okay, and then when you do that, you've got down to here, right? Mm-hmm. Yep. And so what you see then is that the answer is, but hold on, can I borrow your pencil for a sec? Okay, and so, oops, sorry, and then this is, it's really 0, yeah, it's 0 plus x3, 0 minus 2x3, 0 plus x3. So if you write this down at 0, 0, 0, which you can ignore, but plus 1, minus 2, 1, whoopsie daisy, 1, x3, and then we ignore that, so this is just r1 minus 2, 1. Okay, and so what happens is when you do this decomposition like this, you see the solution is a multiple of that one vector. Yep. So yeah, it'd be r like that. And so what that means is its dimension is, in other words, its dimension is a straight line. In other words, the dimension of the solution here is, of the solution is 1. Because it only has one vector. It's any multiple of this. And so that's just a straight line, and that dimension is 1. In other words, there's only one basis vector for that. In other words, any vector on here, on that line, can be described as some number times this. And that's what the basis vectors are, some numbers times that. So that's how you get that dimension. But you said you wanted to think about it, like geometrically, kind of what's going on. Okay. So this is three-dimensional, so this is R3 space. Okay. And it's going to go, because it's a 3 by 3, it means it goes into a three-dimensional space as well. It's a mapping through 3D space to 3D space. Okay, because what happens is 3 by 3, that means the number of columns tells you the input, and the number of rows tells you the number of output, or domain and range space. Okay, so what happens when you solve this, what this is saying is, because you're trying to find, for a given matrix, determine the dimension of the solution. Oh, okay. Okay. All right. So, okay. No, okay. We need to maybe step back a bit from this. Okay. So I thought we were solving ax equal to 0, and that's kind of what that would be the solution to that. Okay. So what that means then is, okay, let's try to think about this. So yeah, what you have just done by doing this process here is solving this equation here. In other words, you're finding all the x values, all the x values that solve this, which is then the kernel. So actually what you've done is said the kernel of A is equal to the span, or any multiples of 1 minus 2, 1. Right? Okay. So what that means is there's kind of a straight line here. Okay. Any multiple of vector on this straight line maps into the 0 here. That's what the kernel really says it does. Okay. So therefore what that now means is, okay, so you know that about the kernel. We also know that the image, oops, hold on a sec, I gotta answer that. The image plus the kernel dimension add up to the total dimension of the space. Okay, let me just see who that was. Rick, you just send it through?
Yep, that should be my test.
Okay, thank you. Yeah, I'll let you know if I got it okay. Okay, thanks. So I'm gonna be answering Michelle's question, Kim's question, and then Dawn has a question, and then if you have some questions, I'll go through those as well.
Okay.
Okay. So what happens is the dimension of the kernel and the dimension of that, the dimension of the kernel and the dimension of the image add up to the total number of dimensions you have.
Yes.
Okay. And so the deal is we had 3, and so if the dimension of the kernel is 1, then the dimension of the image is 2. Okay. So what that means is, and let me try to describe this. Let me actually write it on another piece of paper. It might make it easier. That in this problem, okay, what this means is here's your R3 and here's your R3. So this is your input. What's happening is any part of the vector that lies on that line that we had, this is multiples of 1 minus 2, 1, and I don't know if that's the right direction of it, but let's just imagine it is. Okay. Any vector that lies on here, automatically that part of it gets mapped into 0. So what that means now is if I have an x sitting out here, right, well I can break that x up into a part that lies along that line and a part that lies perpendicular to that line. X perpendicular and x along the kernel.
Yeah.
Okay? We know that so now when you do a transformation, when A acts on x, what A is acting on is on the x perpendicular plus the x that's in the kernel. Right? Because you see, this one vector here can be written as a part that's in the kernel and a part that's perpendicular.
Yeah.
And what we know is that when A acts on the perpendicular, it doesn't go into the origin. And then when A acts on the kernel part, it does go into the origin. So what that means is if you write this out, this gives you AX perpendicular plus AX kernel. Well, we know that this goes to 0, and therefore we know that goes away, and it just gives you that part there. Okay? So what's going on is if you give me any x here, what's happening is the only part that really matters is this perpendicular part, because this part kind of goes away. And so then that is going to map somehow into here. Now, the deal is the image of A is going to be a plane. So there's going to be some plane over here that they all map into. And that's kind of what's going on. So I'm just trying to help answer this question. Given the matrix A, determine the dimension of the solution, okay, and the possible B's that would solve the system. So the dimension of the solution is going to be two-dimensional. In other words, only, actually this is interesting, I'll look it up. Only vectors, I'm trying to think how to say this. Determine the dimension of the solution. How do I want to say this? It's going to be two-dimensional because what's happening is any vector that lies along here, in other words, any part of your vector that lies along here gets collapsed. So the only thing that's going to, when you're going to solve, let me put it a different way. Let's start with the other one. We should probably ask the last question first. What B's are possible to solve this? Only B's that lie in the image. So in other words, B's have to be a member of the image of A. Those are the only B's that are going to work. And to, right, because you see, if you had a vector that mapped you not into that plane, because if this is the image, you know the image is going to be, because the kernel is 1, you know the image is going to be two-dimensional, and so unless that vector B lies in that image, it's not going to work. So the question is, what B is going to be the span of two vectors, right? And you've now got to go through and figure that out. And I remember in my...
It's the pivot variables.
Yeah, it's the pivot variables, and it's the original matrix
From the
vectors
matrix.
from those vectors. So whatever, I mean, I can't remember what our thing is, but it looks like here, it's the first two here, right? So it would be this and that. So it would be 1, 1, 0 and 1, 2, 1. Okay, so that's what would be the possible b's that would solve the system. Any linear combination of these two would solve it. And determine the dimension of the solution. Well, the dimension of the solution is 2, right? Oh, no, sorry. Those are the b's that would work.
Look at the dimension of the image of the solution, right?
Hold on a second. This gives you the b's. Then the dimension of the solution is going to be 2-dimensional as well. It's a good question. Dimension of the solution. Yeah, it's going to be basically it's going to be the same as the number of dimensions here into the image. Should be 2.
So is it always going to be like that? Will it always be that?
No, it won't be. What it will be is the... Let me have a look. I've got my notes. The reason it may not be like that is because if this were R4 going to R3, you've got to make sure, in other words, you've got to take 1, here's the number 1, right? In other words, for your image, you take this dimension and subtract 1. And that gives you how many vectors you're going to need here. But over here, it's got to be 4 minus 1, that gives you 3. That would be the number that you have in your solution. In other words, over here, this is where your solution comes from, because you're asking what x values go to here. So what I'm saying is, how many vectors what's the dimension of the ones you're going to need over here? You basically take the dimension of this space and subtract off your kernel. Okay? Yeah, because they add up. Because of the rank nullity theorem, they add up. Okay, but it's always going to be whatever your kernel is, then that's the thing that then determines what each of these answers are. So, in other words, you know the kernel has a rank of, is one vector. So therefore your image has to be its dimension, 3, minus 1 is 2. So you're going to have 2 vectors that span it. In terms of your solution, it's going to be whatever its dimension of the space is, minus the kernel number. So that, and if it were R4 here, it would give you a 3-dimensional object. Okay, kind of, now normally we only deal with square matrices, so they'll actually be the same. But what to think of is the kernel is the thing that tells you how many disappear. And so, in other words, that's how to think about it. The kernel tells you how many disappear. Okay, and so what that says is over here, if you originally had 4 dimensions or 5 dimensions, whatever you have over here, if one disappears, you're left with so many, that's your solution, because your solution comes from over here. Because your solution is what x values go into this B. So your solution is actually lives in this region, and the B lives in this region. It's kind of how to think about it. It's kind of I'm trying to be very kind of non-mathy about it, and trying to talk about where things live.
It's really confusing for some reason. So I was thinking the same thing. I was thinking the dimension of the solution always matched the dimension of the image. That's not true?
No.
It's the space.
But wouldn't that always be the same?
Minus
If you lost whatever you lose in the kernel is the image, right? Isn't it the same thing? Or what am I
Because they're always going to add up to your
M.
Yeah, but if you had, here's what to think about it is, if this were 4 dimensions here, right, and you're losing one of the dimensions in the process.
Oh, yeah. Okay, I get it now.
That means you have 3 that will go on to B.
Right. So that's your image, right? Dimension of the image is 3.
No. That's the dimension of your solution.
What's the dimension of the image then?
The dimension of the image is over here. That's how big your kernel is over here. In other words, that's how much, whether it's a plane that everything maps into or a line or whatever like that.
Right.
So your kernel is just telling you how many you lose. And it's telling you for your solution space how many dimensions you lose, because you could have a 4-dimensional input.
Right.
And so you lose 1, so you're back at 3. Whereas here, the one thing you do know is that the image of A, the number of, the dimension of the image plus the dimension of that will equal this number up here, this 3 up here. Let's go through it a little bit more carefully.
I think
And I'll go back and check my notes as well, but when you have an n by m matrix, this is really the key to think about it. N is the number of rows, and m is the number of columns. So what that means is m corresponds, because this is x1, x2, all the way up to xm. Okay, so that's your input space. N is the number you have at the end in your image space. What we know is, we'll do the one-dimensional, right? If your kernel of your transformation is 1, okay, what that means is the image here, the image of A, will have a dimension equal to n minus 1. This is the rank nullity theorem. It basically says that this guy plus this guy add up to this guy here.
okay.
So, and so that's to do with what your B's, what your possible B's are that it will go to, that would give you a solution. Okay, you have to have these B's to get the solution. Now I'm going to assume I've got those B's, right? In other words, I've chosen a B that makes it possible to be a solution. Then the next question is, well, when I write down my X solution, how many, R plus S, how many of these am I going to have? The number I'm going to have of these is m minus 1. It's going to be, whatever this dimension of the kernel is, 1 less than that is how many I'm going to have here, which is different from the number here. It is confusing if you... But does that's what I'm trying to answer.
I think I was
now,
misinterpreting whatever that was.
That question?
Probability theorem.
Well, let me just check that I've got that right too. Let me just check. It's been a while.
So I also had, what was it, that the dimension of the kernel
plus
is...
the dimension of A equals n. So it's confusing. It doesn't talk about n.
Hold on.
Something 22.
Oh, hold on. Have I got this wrong? Let me just check.
I just remember having right now the dimension of the kernel of the 3 variables, and the dimension of the image is the pivot.
As n. The dimension of the kernel of A hold on, now I'm having a problem with this because, right, it says that it's not this, right? It says m. Oh, okay, I think you're right. I'll take back what I said.
Okay.
Why am I having a problem with this? I'm having a problem with this and I need to think about this. What I'm concerned about is if this were, say, 20 and this were 3, there's something I'm not understanding here, because if you've got 20 and the kernel is 1, then you would only, now there has to be another theorem somehow that means that this can't happen. You see what I'm trying to say?
Yeah.
That wouldn't work. So this is what I'm this is the problem that I'm thinking about, is that if you now had 20 variables here and you only had 3 equations, I guess the kernel here, there couldn't be one, right? I guess the kernel then would have to be, so there has to be another,
At least 17.
that's right, it would have to be at least 17. And that's interesting, I've never seen that particular theorem anywhere, but that was why I was saying it the other way. But I think you're right, so I'll take back what I said. So what it is, now I'm confused because I don't know the answer to my question, which is, if you now have your kernel here, so you take this dimension and subtract off, and that's the dimension over here. So then clearly this dimension doesn't matter. That's what it's saying.
Well,
But that's really odd.
but it must be because of what we said that you couldn't have.
Yeah.
The solution would have to be at least that many.
Yeah.
You would have to collapse by that many to go onto that other side of the space.
Right, and you just can't have those.
Yeah.
That's what would have to happen. Let's think about the kernel. Oh, remember the kernel is the number of, hold on, what's the kernel?
Number of collapses by.
But the kernel is the number of 3 variables?
Yeah, and the image is
Well then that's how it would work. Yes. Yeah, it's guaranteed that, because it had to be at least 17, because when you have 20 variables and you have 3 equations, you have to have at least 17 for 3.
Yeah.
So that would work. So okay, then I'm good with that. Then I feel comfortable about that.
Okay.
So yeah. So then the answer is, but I'm now still confused.
So in the dimension of just your solution
The solution will match the image of A.
is, that's what I just like.
The solution will match the image of A. Okay. Yeah, I have this. Let me go and get my notes.
Okay.
Because I know I've written down this exact answer to this question.
Yes.
Oh. Okay. All right. Here's how to think about this. Okay. Should have referred to my notes. It would have been easier. Okay. Here's how to think about it. And maybe I actually didn't do this in the video. This might have been the one page that I didn't put in the video. I can't remember. What happens is the following, is that we know how to figure out the dimension of the image, right? You take your original space, subtract off the kernel, and that gives you the dimension of the image. And it's guaranteed to work, not have my problem, so that's okay. Then the dimension, and so basically the question it asks is, what is the dimension of the image? That's what B's would you need? What would be the dimension of that? That's going to be the dimension of the image. We know that. That's going to be 2. And then the dimension of the solution will actually be just equal to the dimension of the kernel. And here's how to think about it. Your solution will be a particular value that solves the problem, plus all of those vectors from the kernel. And let me show you how that works. Okay, if I can, let me show you. Okay. Here's your solution. Here's your solution space, and let's say this is your B, okay? And here is your coming in space. And we've got a single line as the kernel of A, like that. So let's put, okay. So what's going to happen is, there is going to be, from the origin, somewhere around here, a particular x perpendicular that goes from here and maps into your B. There's going to be a particular one that does it. In other words, if there's your line, that one there will map into your B, but that one here won't. They'll go elsewhere. Okay? So that one will map into there. Well, what happens is, because this is the kernel, if I now take a vector in the kernel V, right, and I add these two together, I get this vector up here, x, like that. Have a look at this x. In other words, what I know is ax perpendicular equals b. I know that solves that problem. Now, what about if I look at ax perpendicular plus v that's in the kernel? What's it going to do? Well, it's going to be ax perpendicular plus av, right? And what does this guy go to? It goes to 0 because it's in the kernel, and it gives me this, which, what do I know that is? That's v. So you see what happens is there is going to be one particular thing that maps into B, and then you can add any one of those values of in the kernel, and it will also give you the right answer, because you see this here, a x perpendicular plus v equals b. This is any vector in the kernel, right? In other words, you can add any vector in the kernel to your actual one particular answer, and you still will get the same answer. In other words, this solves it. So you know how we always write down our solution as it's blah plus r blah plus blah blah, you know, like that? What happens is, this is the x perpendicular. It is your actual one thing that solves the problem. What these all are is these are all the kernel of A, because each one of them maps into 0. In other words, it doesn't affect it. This is the only one that determines it. So the dimension of your solution is equal to the dimension of the kernel of A. That's kind of geometrically how it works. Yeah, sorry about that. I had confused myself. This I'm not confused with. This kind of makes sense that that's how it works.
That makes sense. We can write x equals, so whatever you have.
Right. And what you, now actually, what you have here, I'll just point this out, that this is what we usually call the particular solution, because it is the one that actually solves the problem. And these are then called the homogeneous solution, because they solve this equation. Anything that solves an equation, something acting on it gives you 0. It's called a homogeneous equation. And the kernel is what we call the homogeneous equation, the solution.